Let's graph some rational functions using some information that we have already found in this class up to this point. One thing that is helpful is using symmetry, because rational functions tend to have some symmetry in them. You could see that in some of the examples we saw on the previous video. Y-axis symmetry occurs when a function is even. Remember, that happens when f of negative x is equal to f of x. So when you replace every x with negative x, if it simplifies back to the original function, that is an even function and has y-axis symmetry. This is not what I wanted there. You can't have x-axis symmetry for any function because it won't pass the vertical line test. It will fail the definition of being a function. What I meant here was origin symmetry. And that happens when you have an odd function, which is when f of negative x is equal to negative f of x. If you remember those definitions from a while ago. Some functions are neither even nor odd. They won't have either of these symmetries, and that's okay. It tells us something too about the graph. Find the intercepts, always. We always want to know the x and y intercepts of a function. Find the asymptotes using the techniques we just talked about in the previous video. And then you'll need to plot some extra points, and then do your best to sketch the curve. Let's try these steps in this function. Let's first check for symmetry by plugging in negative x in place of x. 3 times negative x squared minus 3 over negative x squared minus 4, which is 3x squared minus 3 over x squared minus 4. That is equal to the original function, right? When you square negative x, you get just x squared. So in both cases. So we get the original function. That means this is an even function. And we have y-axis symmetry. That's nice because that means we can get half of this function and be done, right? We can just do a mirror image to the other side. If we get the right side of the function, we can then know what our left side looks like. Step 2 is to find the intercepts. Let's see how much space. Oh, I have a whole page here. Okay, just want to make sure I left us enough space to work here. I was trying to kind of cram it in, but we can make a little more space. All right, intercepts. Let's start with the y-intercept. F of 0. Plug in 0. That's 3/4. So the y-intercept will be the ordered pair 0, 3/4. The x-intercept is when the function is equal to 0. There's two ways you can think about solving this. First of all, the only way for a fraction to equal 0 is if the numerator is 0. The other option, meaning we could just set the numerator equal to 0. The other option is to say, you know what, I like to see it algebraically. Multiply both sides of this by x squared minus 4. And you end up getting 0 is equal to 3x squared minus 3. Because these simplify, right? I like to factor. Because then you avoid any temptation of wanting to divide by a variable. We don't like dividing by variables. This means x equals 1 or x equals -1. So my x-intercepts are 1, 0, and -1, 0. Remember, when we want to find the x-intercept, we replace the y, or the function notation, with 0. So that's how we got those. I am going to go ahead and plot those. Because we've got some fractions going on here, and relatively small numbers, I'm going to give us a little bit more space by doing going by twos. So this will be 1, 2, 3, 4, and so on. -1, -2, -3, -4, -5, and the same here. 1, 2, 3, 4, 5. Okay, my y-intercept is 3/4 of the way between 0 and 1, so it's going to be here. And then I have an x-intercept at 1, 0 and at -1, 0. So I have those 3 points is what I have currently. I also know that is nice. It still matches my symmetry, right? If I have 1, I need -1. Step 3 above is to find the asymptotes. That also tells us a little bit about the domain of this function, so that's pretty nice. The asymptotes, we're talking about vertical asymptotes. Remember, we want to know where the denominator is 0. That would happen when x equals 2 or x equals -2. I know, well, let's rewrite this function. I'm going to factor the numerator just to make sure we don't have anything canceling. When we worked on the x-intercepts, we found that that numerator factored into 3 times x minus 1 times x plus 1 there. Gosh, that's messy. The denominator factored into x minus 2 times x plus 2. So nothing can simplify away. So these are indeed vertical asymptotes. Let's put them in on our graph. At 2, I'm going to put these dashed vertical lines. And at -2. Okay, we need a horizontal asymptote, or find if there is one. Remember, we need to compare the degrees of these. The degree of the numerator is 2. The degree of the denominator is also 2. When they are the same, we look at the ratio of the leading coefficients. My horizontal axis will be x equals 3 over 1 or x equals 3. Let's go back up here. Let's put that in. That's here. So now I have a horizontal axis there. Okay. Then it says plot extra points. You will need them. So we need to know what's really happening here on the outside of the axes and between the axes. So I'm going to plot some extra points to help me do that. Sometimes a table of values is nice for this kind of thing. I've got some good points in between the asymptotes. I think, based on what I'm seeing here, because the function has to approach the asymptotes, the vertical asymptotes, and can never cross a vertical asymptote, because if it crossed a vertical asymptote, that would imply that it was defined, that the function was defined at those x values. And the function cannot be defined at a vertical asymptote because that's where you get 0 in the denominator. So that is not okay. So no crossing vertical asymptotes. It's not allowed. Because of that, and the shape that I have here, I'm thinking I'm going to have what kind of looks like a parabola. It's not a parabola because it's bounded by these asymptotes, and parabolas are not. But I'm thinking I'm going to have something that does this. If we want to make sure, maybe we should figure out like f of 1.5 and negative. Well, actually, I don't need to do negative 1.5 because I have symmetry. I don't need to do both of them. Once I have 1.5, I know that negative 1.5 gives me the same result because of the symmetry over the y-axis. And I also want to do some other points. So I'm going to do like 3 and 4 here. This could get a little complicated plugging these in. You can do it if you want. I'm going to use the table feature in my calculator, but you can certainly do this without that. Let's go to the y equals. I'm going to clear this out, and then I'm going to put this function in parentheses for my numerator. What is my numerator? 3x squared minus 3, right? 3x squared minus 3, denominator x squared minus 4. All right, let's go 3x squared minus 3, and then divided by, and I need parentheses around this so that it divides by this whole thing, x squared minus 4, parentheses. Graph it, and that kind of gives us a picture. But the graphing calculator is not great. Let's zoom standard, number 6 there. So we kind of have this picture. That helps us a little bit. What I wanted to do was use the table and type in this 1.5, and also 3 and 4 were the other ones I wanted to know. So we're getting an approximation here, negative 2.143, 4.8, and 3.75. Negative 2.143. 2.143. For 3, we got 4.8. And for 4, 3.75. So let's graph those. 1.5, approximately negative 2.143. So we're going just a little bit below 2 here for 1.5. So down here. Remember, our symmetry allows us to put the same point over here at negative 1.5. That to me gives us a pretty clear picture of what's going on. I thought that's what was going on before, but just to make sure. It's hard to graph on here, sorry. One thing that is important, this function that I just graphed has to approach those those vertical asymptotes. Let's take a look at these values. When x equals 3, y is 4.8. That is up here almost to 5, almost off the graph, right? And when x equals 4, y is 3.75. So we have this picture. We do know that we have to approach the vertical asymptote, so this is going to go up like that. We also have to approach this horizontal asymptote. By symmetry, we get the similar picture on this side, and you could be very precise, but I'm just going to, for sake of time, just kind of reflect that over there. So that's the graph of this rational function. We did need a few extra pieces here to show us, a few extra points, but that symmetry really helped us to recognize that this also works for -1.5, -3, and -4 as far as those x values. Get the same y values. So use your tools that you know. I decided we are going to skip slant asymptotes, so you can either throw this page away or hang on to it, whatever. Just leave it blank for now. The last thing we're going to talk about with rational functions is this application. A drug is injected into a patient and the concentration of the drug in the bloodstream is monitored. The drug's concentration C of T in milligrams per liter after T hours is modeled by this function. C of T equals 5t over t squared plus 1. The graph is given in this picture. Okay, use the graph to obtain a reasonable estimate of the drug's concentration after 3 hours. Well, looking at the information that we're given, T is the independent variable. C, concentration, is the dependent variable. So time is independent, concentration is dependent. After 3 hours, that means we're looking at when T equals 3. So I'm going to come up here, and it appears to be 1.5, right? Halfway between 1 and 2. So it appears to be approximately 1.5 milligrams per liter is how much drug is in this person's system, this patient. Use the functions equation to determine the drug's concentration after 3 hours. Well, that means we just plug in 3 for T, right? C of 3, 5 times 3 over 3 squared plus 1. That gives me 15 over 10, which is indeed 1.5 milligrams per liter, or 3/2 if you prefer the fractions. Last question here says, determine the horizontal asymptote of the function and describe what this means. Well, looking at the picture here, I'm not really sure what's happening. The horizontal asymptote would be as this function goes forever this way. We're talking about x going to infinity, or I'm sorry, not x. T is our independent variable. The horizontal asymptote is talking about that independent variable going to infinity. What is that approaching? Well, it's easiest to look at it and figure that out by analyzing the actual function, not just the graph, because I'm not sure that the graph is super clear about that. To find a horizontal asymptote, we compare the degree of the numerator with the degree of the denominator. The degree of the numerator is smaller than the degree of the denominator. In that case, the horizontal asymptote occurs, oopsie, not when T, when C is equal to 0. Since degree of numerator is smaller than degree of denominator. Okay. Coming back up here, that means there's going to be a horizontal asymptote here. So that graph, as it continues, is going to continue like this and eventually approach this horizontal asymptote. The interpretation of that basically says, as time continues to pass, the concentration of the drug will approach 0, which is what we would expect, right? As time passes, the drug wears off because it gets absorbed by the body. It gets absorbed in by the liver and the kidneys, all filter stuff out, right? So that is the interpretation of what is happening and why this approaches a horizontal asymptote. That's our study of rational functions. We are going to look at rational functions still more in the next video, but that kind of describes what they look like and how you graph them, how you can use them, and how they show up in a real life situation. This is a very common situation for drug use, concentration.